Okay, great. So as Mason just said, I'm Sloane Sirota. I am a PhD student at WVU, and I am here to talk to you about my work, trying to answer the question, do all fast radio bursts repeat? Now, in the last talk, they gave a really great background about R1 and, talking about, they also mentioned the question, do all FRBs repeat? There are some people that say yes. There are certain progenitor models that could account for both repeating and non-repeating, or that could account for repeating sources and non-repeating sources being the same. There is some analysis that has shown some type of link between their energy distributions. And also, there is the big question of, maybe this is just an observational bias, the fact that we're seeing so many differences between the two populations. On the other side of things, we have people who say, no, they're definitely not the same population. Hyperactive repeating sources are a very big argument on this side because, how do you account for both hyperactive sources and these so-called one-off sources coming from the same place because they're exhibiting such different properties. Machine learning algorithms that are, or blind machine learning algorithms have classified them as two separate populations. So that's just based off of statistical testing. And there have been many, many papers that have shown that there are distinct morphological differences. This being said, there's still a very, very large debate around this topic, and we're still trying to get to the bottom of this. So, following the analysis done in Yamasaki et al., a paper published in 2024, I'm attempting to shed some light on this question. So first, we're going to infer the CHIME selection function, which I'll get into in a minute. Then we're going to assume a power law burst rate distribution. Then, of course, we run our simulation. And then after that, we're going to see, okay, did it work? And then we're going to talk about the next steps. So first, we're going to infer the CHIME selection function. So I do want to give a disclaimer. This is not quite as in-depth as the talk that you will see from Kyle. I believe he's 2 more talks after me, so you'll get a bit more information from him. But we are attempting to find a simple yet still rigorous way to account for the CHIME sensitivity and CHIME exposure as a function of declination. So first, we assume a uniform all-sky distribution. We assume that, everywhere in the sky, same number of FRBs, and we assume that it's a constant number of FRB sources in the CHIME sky. These assumptions are important. These are foundational assumptions in this analysis. And then we can compare this with the CHIME detections. And then from there, we can plot the CHIME detections as a function of declination. Now, we know that the CHIME sensitivity and exposure both scale with declination. So we compare the CHIME catalog 1 detections with what we would expect to see from a uniform all-sky distribution. And out of this, we get what we call the selection function. The selection function is basically a measure of the probability of the CHIME telescope detecting an FRB given its declination. So that plot all the way on the right shows you what we get out of this analysis. We are using a polynomial fit. And so this is how we scale our simulated FRB detections. So now we need to figure out, okay, we have this scaling that we're going to use. So what about the burst rates? How do we determine that? So following Yamasaki et al., the paper I mentioned before, and Gardinier et al. In 2020, we will assume a power law burst rate distribution. What this means is the number of sources with a given repeating rate scales as that repeating rate with some power law index that is one of the parameters we're trying to find. So the repeater rate we take as bursts per hour. In that top plot, I show one of the plots from a CHIME paper on repeaters to show you that these burst rates kind of range from a max of like 10 bursts per hour, and they go down to 10 to the minus 2 bursts per hour. To kind of give you an idea, we're working in log space here. So now we have our burst rate distribution that we're going to now use to simulate our population of FRBs. So now we're going to run the simulation. So our simulation, we're trying to fit for 3 parameters: the minimum repeater rate, or the minimum burst rate that a repeating source can have. We call that R min. We were also fitting for R max, which is, the maximum repeating rate that a source can have. Except we found that it makes just about no difference in the range where you would expect R max to fall. So we just set it to an upper limit of log 10 of R max equals 1, aka 10 bursts per hour is the maximum repeating rate that you can find. And then we're fitting for that power law index that I mentioned. And then we're also attempting to fit for the number of FRBs in the CHIME sky. So unfortunately, I wish that I had a better set of results to show you. Anyone who's ever run an MCMC knows that this is not what a trace plot should look like. Anyone who hasn't run an MCMC, let me tell you right now, that is not what it should look like. What you're usually looking for in these trace plots is for all of these little walkers, all the lines to converge to one point, to show you that your model has settled on one set of parameters that is the best fit for your whatever you're trying to fit. So unfortunately, in time for this talk, I was not able to get a set of parameters that my fit would converge to. However, it's okay, because we can still look at kind of the average of these. I am giving you guys the disclaimer. This is not something that this model converged to. I'm giving you the average of where all these walkers are kind of landing. So don't ask me for like chi-squared or anything. It's a touchy subject. So can we find values that match the CHIME catalog 1 data? So I'm giving you the, once again, in quotes, best fit parameters. This is where our walkers kind of land. As you can see, we have a relatively good match for the CHIME parameters, or the CHIME catalog 1 data, with the top lines being the total number of bursts that we see, the blue line being all of the repeating bursts, and the orange lines being all of the first repeats. So the first time we've seen each repeating source. The dotted lines are the simulated values, where the solid lines are the CHIME values. So a plot like this kind of shows that the lack of convergence is not necessarily due to the fact that, this is just a terrible model. So obviously the lack of convergence is never a good sign that your model matches whatever data you're looking at, but it's highly likely that there is an issue in the way we are calculating our log likelihood, something that I'm working on. But if you look at, once again, if you look at this plot, it shows that there is some merit and there is some hope for this model, and the fact that one day it will converge. In fact, if these are the parameters that don't converge, just imagine how good it'll look when they do converge. So this would predict approximately 100,000 FRBs in the CHIME sky. And also the R min value, I know that 10 to the minus 4.8 bursts per hour doesn't really make the most sense. You don't think, yes, 10 to the minus 4.8 bursts per hour, I did the math. That would be 1 burst every 50 or 60,000 hours. So that would be the lower end of our repeater rates, just to give you kind of a sense of the scale that we're working with. So now, next steps. Obviously, next step number 1, we're gonna fix our likelihood function so that it doesn't keep getting stuck. But As you'll hear in the next talk, there's a lot coming with CHIME Catalog 2. So a huge thing to look for would be, does Catalog 2 follow our fit parameters for Catalog 1? So if that matches, that would give a lot of merit to the idea that, you know, maybe this is just one really big population of all repeating sources. Another thing that we are going to do in the future is maybe look at different burst rate distributions. While, you know, we could argue that they might all repeat, we could then say, you know, are we drawing from the correct distribution? We could look at instead maybe a log normal distribution, which has been used in other analyses. We also, I forgot to mention, sorry, we use a Poissonian wait time distribution between our simulated bursts. This is not necessarily what is observed for all bursts. A lot of bursts do assume a Poissonian or pseudo-Poissonian wait time distribution, so the time that you see between repeat occurrences, but some have been better fit by a Weibull distribution, some exhibit some type of burst memory. So these are all things that we might further incorporate into our simulation. And finally, the question of the hour, do all FRBs repeat? I wish I could give a more satisfying answer than maybe. So thank you, and I can take any questions.
Hi, Sloane. Great talk. I'm Kyle McGregor. I'm a master's student here at McGill. I was curious if you account for like fluence incompleteness at all, because there's this theory that the apparent one-off bursts could just be the brightest bursts from repeaters that have some energy distribution that we're only detecting the high tail of. So do you account for like sources that could emit bursts of too low energy for us to actually detect with CHIME?
Great question. So we actually kind of, in a way, sweep under the rug like fluence information and the energy distributions, because we're not assuming anything about morphology or anything. We are saying this is the number of sources that are visible to the CHIME sky. They repeat at this rate. We have at one point we have like a random number generator to kind of mimic that like randomness of the detection. But we don't directly take into account anything like signal to noise, fluence, anything like that.
We'll move on to a question from online.
Thanks. So I'm gonna, this has been written in the chat from Aniket Prasad. Hello, Sloane, excellent work there. I was curious about the plot of simulated versus FRBs. I see an abrupt looking jump around 1200 hours for the first repeat, sorry, the orange dotted line. Is there any physical reason or simulation assumption behind it? The total FRBs dotted line also shows a similar sudden jump.
Great question. There is no reason necessarily that we would expect that jump. The jump is likely a statistical fluctuation because some of the runs don't have that jump, some do. I thought that this was a good plot to kind of represent overall the model. So if I showed, I could pull up another plot and it wouldn't necessarily have that jump. I think it's a bit of a weird coincidence, but it does come up every once in a while.
Thank you.
Hey, Barak Zakai asking. So the original argument about whether FRBs repeat or not was better articulated by Shri. You can't kill a star for an FRB. The rate of FRBs is larger than the rate of forming stars. And it seems that it was missing from the discussion in. So maybe, can you relate to this? Are we still talking about this?
Sorry, could you repeat the question?
Okay, I'll try to phrase it sharply. What is the all sky rate of FRBs above some, you know, you define the fluence. And is it larger or smaller than the rate of, let's say, supernova or something?
Yeah, I can't comment on that. I've not, I don't know the all-sky rate of supernovae or star formation. I also don't know that these parameters are necessarily the best ones. So I think that once we get our fit to converge completely, we would be able to say more about like the total number of FRBs in the sky, the all sky rate, because I think that this is kind of just trying to show what we could get out of our fit. But I don't necessarily know that 100,000 FRBs in the sky is, you know, where we're going to settle. Does that answer the question?
Okay, I will leave it there for now. Let's thank Sloane again. Okay, and next we have Jain, who's a student here at McGill, who will be talking about the, well, let me wait for the slides to pop up first. Also, I encourage folks, if you have more questions for the speakers, feel free to just ask in the Day 2 Slack channel.
Sorry, this is yours, eh?
Yeah.
Wait.
Is the screen shared appropriately?
I think so.
Okay, good. Okay, so in the next talk will be by Jain, a student here at McGill, who'll be talking about the second CHIME FRB catalog.
Can everyone hear me? Okay. So my name is Jain, and I'm a master's student at McGill. And I'm here to present the second catalog of fast radio burst on behalf of the whole CHIME FRB collaboration. One way to tackle the physical enigma that are fast radio bursts is to collect a large sample of bursts and then hopefully use that sample to answer some of the fundamental questions that were mentioned in the previous talks, such as what is the FRB luminosity function, whether or not all FRBs repeat, are there different classes of FRBs within the population, and what is the volumetric rate of FRBs. It's also having a large population is also useful in identifying unique FRBs that stand out from the general population, and also can be used to retrospectively cross-match with other transient catalogs to find multi-wavelength counterparts. Ziggy Plunis yesterday gave a great talk on the CHIME FRB instrument. I want to highlight again that CHIME is a great FRB hunting machine, owing to its large field of view of over 200 square degrees. It also observes about a wide bandwidth from 400 megahertz to 800 megahertz, and it observes the entire sky above a declination of -10 degrees every single day. And that allows us to see a lot of FRBs. In catalog 1, we presented 474 non-repeating bursts and 18 repeated sources observed between July 2018 and July 2019. In catalog 2, we have increased this number by an order of magnitude, and we're going to be presenting 3,649 apparent non-repeaters and 83 repeating bursts, a sum total of 4,547 bursts observed between July 2018 and September 2023. So what do we provide to the community in the upcoming data release? For every single burst, we will be providing a total intensity dynamic spectra from 400 to 800 megahertz, with a time resolution of 1 millisecond and frequency resolution of 24 kilohertz. We also provide localization estimates, typically within 10 arc minute. Note that the localization regions are quite complex, but we do provide the full confidence intervals. We also provide the detection signal to noise ratios, burst cosmology models that include parameters such as burst width, scattering time, spectral index, amongst others. We also provide the sky exposure for each sky position and fluence and flux limits, fluence and flux measurements, as well as instrument sensitivity to each burst in the catalog. A bit about exposure. For CHIME FRB, the exposure is defined as the total time each sky position spends within full width half maximum of CHIME beams at 600 megahertz. When calculating exposure, we exclude periods of system shutdowns or reduced sensitivity. Over the catalog 2 time period, the system uptime was about 76%. In the plot here, I'm showing, the plot here shows exposure as a function of a galactic coordinates, and a typical sky location in the field of view has about 100 hours of exposure. Note that the regions above a declination of 70 degrees are circumpolar, and so we observe those twice a day in 2 different transits, and we code an exposure for each of the transits separately. The exposure also varies as a function of declination, with the North Celestial Pole having exposure of up to 10,000 hours in total. On average, CHIME observes about just under 2 sources per day with a signal to noise ratio of above 10. In the plot here, I'm showing the number of sources per day observed as a function of time bin by the month of the year. And we see some variability over here, and that's typically due to system shutdowns, updates, weather, or RFI environment. We have also done significant amount of consistency checks to make sure that other factors are not affecting the source rates. So for example, time at which the burst is detected, weeks, months, but the most significant contribution, or the most significant dependence, was on galactic latitude, which, although I would note that latitude-dependent observing effects, such as system temperature variation or galactic DM, have not been corrected for here. We also provide burst properties, like flux influences, because we assume that because we assume in this calculation that the burst is observed at the bore site. These are strict lower limits, and any analysis using fluxes influences should take that into account. We also have not been able to provide flux influences for about 400 events due to calibration or RFI issues. And we did some consistency checks to make sure that this does not introduce biases into future analysis using this data. And we find that bursts with missing fluences tend to be a little wider and highly scattered compared to the general population. We also see morphological differences that were reported in Plutus and et al. In previous work based on catalog 1 sample. More specifically, that repeating sources tend to have narrower bandwidths and larger burst widths. On that, there's a lot of ongoing and planned projects using this data. To highlight some, we are going to be soon also providing full baseband data for a subset of this sample. There's also going to be a new repeater catalog. big shout out to Kyle McGregor, who will be talking about the CHIME FRB selection function in next talk. And I would also encourage people to look out for talks by Lodrick Kahinga and Swarali Patel on constraining M31 DM contribution and spatial dependence of FRB detections in the CGM and correspondency section on Thursday, as well as some work done by Vishwangi Shah on characterizing the lower bound on maximum FRB energy, and Hao Chang Wan on galaxy power cross spectrum. To summarize, the second CHIME FRB catalog presents the largest uniform sample of FRBs to date. The data release includes raw intensity data, as well as various burst metrics. We observe roughly 2 FRBs above signal to noise 10 every day. And we have done a lot of sanity checks to characterize biases that may influence future analysis using this data. And I would like to emphasize that this is a collaboration-wide effort that took a lot of teamwork and perseverance to get this data out to the public. Thank you, and I'll take any questions.
Pick the one in front first.
Thanks for the really interesting talk. I'm Pawan from Swinburne. I was just curious about the number of candidates in the subthreshold region. If, for example, you have so many sources, how would that scale above a SNR of, say, 8?
I'm not sure if I know the answer to that, although, yeah, I'm sorry, I don't know the answer to that.
Kelly Gordy from CSIRO. Looking forward to seeing the results from this. Really nice. I was wondering whether the instrument or the search pipeline or the detection pipeline has changed significantly from the first catalog. Because I'm wondering, for certain statistical analyses, whether this can be combined with the first catalog or whether there's some caveats.
So there were some changes to the RFI sifting algorithm and the dispersion algorithm in the system. I don't remember on top of my head when that happened in this timeline. But also there were changes made to the fit burst model. And there's an elaborate section in the paper discussing how that, this is not the latest slide set, but there is an elaborate section in the paper that discusses how that update to fit burst model affects parameters like spectral running and spectral bandwidth.
Okay.
Oh, yeah.
Oh, okay. Okay, so you've gone and reanalyzed.
Oh, yeah. So the new catalog includes catalog 1 burst as well.
That's important. Okay, thanks.
Any other questions? One quick question, Marcus.
Hi, Marcus Lower from Swinburne University. This is awesome work. Could you say a little bit more about the morphological features that are being included in the catalog, aside from just widths and spectral indices?
So we have burst width, scattering time, DM, best SNR, spectral running, spectral index. Those are on top of my head.
Awesome, thanks.
Okay, we'll leave questions there and let's thank Naman again. Okay, the final talk of this session is by Kyle McGregor. It's a 3+2 talk. I'll give you a 1-minute warning, not a 5-minute warning.
Thanks. Yeah, just 1 second to get his slides up. It was open one of the. That's not you, is it? No. Just a second, we might need to get his slides up again.
At the top.
Yep. Yep.
Spoiler alert, jeez.
Great, yeah. McGregor is a grad student here at McGill, and he will talk about selection function.
Thank you. Yeah. Perfect. Yeah. Yeah. I'm Kyle McGregor. I'm a master's student here at McGill. Yeah. Thanks for the shout outs in the previous talk. I'm really excited to talk about my selection function analysis for catalog 2. So it's worth saying that the sample of FRBs that CHIME FRB detects is inherently incomplete. And what this means is that essentially every burst that we detect has some probability of detection by our instrument. So for example, there's a burst on the left here, yeah, that's the left, which is very narrow in time and very bright. And this is like the prototypical type of burst that CHIME FRB would detect. So the probability of detection is very high. But kind of phenomenologically on the burst in the right is much more wide and scattered. So while it might have a similar affluence, its probability of detection would be lower just because it's harder for our pipeline to detect as it searches. And so the function, I guess, that maps this like universal FRB population, which includes all of these morphologies, to what we actually observe is what we can refer to as the survey's selection function. And we want to kind of put numbers to this concept. Not yet. Okay, so the way that we do this is CHIME FRB has this injection pipeline that allows us to directly probe the selection effect in the FRB parameter space by injecting mock FRBs into our real-time search algorithm and determine what their detection status is, so above some SNR threshold that we set. We did this in a large run that took about 10 days in the past March, of about 500,000 injected events, which is nearly an order of magnitude more injections than was done for a similar catalog 1 analysis, except we're approaching it a bit differently. With this, we're modeling the selection function explicitly using a smooth functional form that can assign a 0 to 1 detection probability all across the 4-dimensional parameter space of fluence, scattering time, pulse width, and DN. And for this, we use a logistic regression formalism. So this is a 4-dimensional function bounded between 0 and 1 in the range. So the way we can visualize this is through slices of it. So here is just a 1-dimensional slice of the scattering time detection probability, holding width and DM constant and varying the fluence. So this is increasing the fluence up. We can see that our detection fraction increases. And then we have this kind of decision boundary that approaches to higher scattering times at higher fluences, which is what we'd expect for sources that are easier to detect. And I'll just keep playing this, but I'll also play the one on the right, which is a 2-dimensional slice of this selection function, which is fluence and scattering time varying the width and holding DM constant. And what we can see is this curved decision boundary covariate between fluence and scattering time, which is what you would expect for these two parameters. But what you also see kind of at the beginning of this is this dip in detection probability at moderate to high fluences between 100 and 1,000. And this is kind of a new discovery that we found, that there's a slight dip in CHIME FRB selection at moderate to high fluences, likely due to our RFI masking. So this is great because we can use this selection function across our parameter space to selection correct our catalog 2 distributions, basically by weighting them up, weighting each burst up by their detection probability. And once we have a selection corrected distribution, we can compare this to the actual catalog distribution, and this allows us to improve our intrinsic rate estimate for the sources detected by CHIME FRB. And just a note for the community, it is kind of desired in population modeling of FRBs to have some kind of probability of detection by an instrument to do population syntheses and other similar analyses. And this is essentially that. So once this analysis is out, I would encourage the community to use it for refining model FRB populations. So thank you all, and I'll take any questions you have.
We have time for one quick question for Kyle.
Hi, I'm Max. I'm a master's student at Amsterdam and an incoming PhD student at McGill. Kyle, on your two-dimensional slice figure where you think you had scattering, yeah. Why do you reference scattering at 1 gigahertz frequencies?
Well, it was so the question was why we reference our scattering times to 1 gigahertz. This is actually a good point. So usually in the community, it's referenced to 1 gigahertz, although in catalog 1, it was referenced to 600 megahertz. And in catalog 2, it's actually referenced to 400, I think. It might be the other way around, though, but I think it's that. So this is just a way of being consistent across instruments and parameters.
Okay, let's wrap it up there, and let's thank Kyle and all the speakers in the session. We have coffee break until 11:05, but before there's an announcement by Amanda.
Yeah, so those of you who have been in the transient field for a little bit might have heard stories of buttons at the Great Debate. So for GRBs, there was this great debate of whether they were galactic or extragalactic, and they handed out buttons to mark what we all bet on. So we wanted to do something similar for this conference, and given the topic of the discussion today, we thought it'd be cool to make people pick a side on if all FRBs repeat or if there are repeating and non-repeating FRBs. So though we will find buttons outside, we encourage you to pick a side and spark a lively debate with someone who disagrees with you. And if you cannot choose between the two, we have a third option for the fence sitters that there are N populations of FRBs. And with that, enjoy your coffee.
Hi everyone, I hope you all are having a great time at McGill. I want to thank all the organizers for having me here to talk about the fast radio burst host galaxies and the corresponding implications for their progenitors. Let me begin by a brief overview of the discovery of the very first FRB. So the first FRB was discovered in archival data from 2001, August 24, in 1.4 gigahertz survey of the Magellanic Clouds using the multi-beam receiver on the Parkes Radio Telescope in Australia by the amazing team of astronomers including Dunk Lorimer, Maura McLaughlin, and Matthew Bales. This first burst, also called the Lorimer burst, was detected with a less than 5 millisecond duration and about 30 Jansky flux density. Building on the discovery of this Lorimer burst in 2007, Thornton et al. In 2013 reported 4 new FRBs detected using again the Parkes Radio Telescope, all with millisecond durations occurring at high galactic latitudes, thus providing compelling evidence that FRBs are indeed real. Since then, the FRB community has been building up larger samples of FRBs, suggesting that most of them are bright about Jansky scale flux densities. They are also brief with less than millisecond durations. About 90% of the population is apparently non-repeating, and most of them are actually extragalactic in origin. The all-sky rate of FRBs is actually quite high, which is 10 power 5 per sky per year. The dispersion measure of the very first FRB, the Lorimer burst, was about 375 parsecs per cc, which was far larger than that of the Milky Way contribution, which is the primary reason why we thought it was extragalactic in origin. And in fact, most of the FRBs that have been discovered to date have hundreds to thousands of dispersion measures. However, the localization of all of these FRBs are about arc minute across, which makes it difficult for us to pinpoint a certain direction where the FRB may be coming from in the vast universe. So gradually we realized that given these repeating bursts of a certain number of FRBs, we may be able to do VLBI observations to identify their origins. So thanks to the interferometric capabilities of the VLBI, we were able to localize FRBs with repeating bursts with milliarcsecond precision to extragalactic distances. The first repeating FRB R1 was localized to a dwarf star-forming galaxy at about a gigaparsec. The galaxy itself had a low metallicity, And the FRB source was also coincident with this dwarf star-forming knot in its host galaxy, and it also had a compact persistent radio source associated with it. So overall, the storyline here was very consistent with a young magnetar formation channel expectation, such as that of a core collapse supernova. FRB 2018-0916b was localized at an offset of about 250 parsecs from the nearest star-forming region in its Milky Way-like galaxy. This instilled several questions in the community around whether or not this spatial offset itself is consistent with the migration of the source from its birth site in the star-forming region to its present location where the FRB occurred within the magnetar magnetic field decay timescales. So could it involve a delayed formation channel or a formation channel that involves kicks? It wasn't very super clear at the time. FRB 2020-0120E was then localized to a globular cluster of MET1 in our own neighborhood at a distance of about 4 megaparsecs. There was no clear persistent radio source or a prompt radio counterpart associated with the same. However, regardless, it still challenges the young magnetar origin of formation channel because globular clusters are known to have old stellar populations. So at this point, I'd like to emphasize that in these early days of the FRB science, our localization capabilities were largely limited to FRBs that exhibited repeated bursts to some extent. One of the dream scenarios for anyone working on understanding the progenitors of FRB sources came true back in 2020 when an FRB-like burst was detected from a magnetar in our own galaxy. So both CHIME and STARE-2 reported detection of a weak FRB-like burst, which was also temporally coincident with a hard X-ray burst detected by CONUS wind from SGR 1935 plus 2152. So based on this detection, the implied detection rate of hard X-ray bursts and radio bursts similar to the ones observed from SGR 1935 was estimated to be about once every 25 mega-years for a magnetar. Further, deep continuum follow-up observations at X-ray, radio, and infrared wavelengths revealed the existence of a supernova remnant at approximate location of the magnetar. And proper motion measurements of the magnetar when extended to the expected age of the supernova remnant of about 16 kiloyears, so it's a fairly old supernova remnant. It resulted in concluding that the magnetar itself, which is this bright object here in X-ray, is consistent with being originating at the centroid of the supernova remnant shown in red from radio observations. So this particular FRB strengthened the association of FRBs to magnetars. However, we must note that most of the FRBs occur at extragalactic distances where such detailed and resolved studies of the source itself are not really possible. So that requires us to build larger samples of FRB host galaxies where the stellar population properties of the galaxy could be harnessed to learn about their progenitors. All of us here have been working together in parallel towards a common goal of building larger samples of FRBs with sub-arc-second localizations to tackle the question of dominant FRB source formation channel. Several instruments here are playing a key role in the game of FRB discovery and localizations. Most of these FRBs are actually also non-repeaters, so their arc-second localizations upon detection is actually indeed a massive feat, all thanks to all these instruments including DSA, ASCAP, CHIME outriggers, and MeerTRAP. Here I'm showing cutouts of FRB host galaxies published to date from all of these instruments. And honestly speaking, to me, the real indicator of success was the amount of time it took for me to compile this gallery of images, because it literally took forever. There are so many FRB host galaxies that are published so far, and I'm so proud. So we have followed up each of these FRB host galaxies to obtain their spectroscopic redshifts. In addition, we jointly modeled the observed spectroscopic and photometric observations to fit their spectral energy distributions and extract their stellar population properties. Using the measurements reported by several groups, such as the ones led by Shivani Bhandari, Alexa Gordon, Mohit, Casey, and myself, and comparing them with the background galaxy population modeled in the same fashion in 3 different redshift bins, Alexa concluded that FRBs trace the star-forming main sequence of galaxies. There were a handful of quiescent hosts like the ones right here, but there was no clear correlation with large galactocentric offsets, so it's difficult for us to comment on whether or not there's a preference for delayed formation channels for these specific hosts. In fact, most of these FRB host galaxies have a fairly active star formation history over the past 102 giga-year, which is a timescale that we can actually probe with existing observations. Upon carefully comparing the FRB host galaxy population with core collapse supernovae, we found that there's an approximately 3 sigma deficit of FRBs in low mass galaxies. So the triangles all here in the background of this DM versus R band magnitude plot are core collapse supernovae, and all these other points are FRBs. So clearly there's a deficit of FRBs in host galaxies with mass less than 0.1 L star. There's only a handful even if you extend the redshift a little beyond. Now, there could be several ways of interpreting this in the broader context of magnetar formation. So owing to the positive mass metallicity correlation of galaxies, this may imply a preference for higher metallicities, and this is in principle very similar to, say, long duration GRBs and superluminous supernovae, which prefer low metallicity environments to prevent wind-driven mass loss, thus supporting the formation of a black hole at the end of its lifetime. Other ways could be a preference for a combination of stellar mass and star formation rate, as was presented by Nick and Horowitz et al. 2025. All of these possibilities still remain open. So far, the entire discussion has mostly been around the core collapse supernovae formation channel. However, we know that FRBs do exist in different environments such as globular clusters, elliptical galaxies, and dead spiral galaxies. So in principle, FRB host galaxy properties are still consistent with any transient class that traces star formation rate to some degree, for example, type 1a supernovae or short duration GRBs. So these two transients are often invoked to explain similarities with NSBH mergers, BNS mergers, binary white dwarf mergers, or accretion-induced collapse of white dwarfs. And there have been several works in the past that have indicated that it's possible to get FRB-like emission from all of these formation channels as well. In fact, if you compare stellar mass of host galaxies for all of these transient classes, the similarities with type 1a supernovae and short duration GRBs cannot really be ruled out at a 3 sigma level. Independent insights on the formation channel can be obtained by looking at high resolution imaging of the FRB host galaxies. Alex Mannings and Michele Woodland compiled a sample of HST observations at UV and infrared wavelengths, together with ground-based adaptive optics aided imaging from Gemini South. So here I'm showing an example of the FRB host galaxy imaged using HST versus ground-based imaging. They found that FRBs may occur at moderate offsets from the galaxy centers and on fainter parts of the IR profile or in regions of higher than average stellar mass surface density. Both of these studies observe that many hosts exhibit spiral structures and FRBs often lie somewhere near spiral arms, but it wasn't statistically quantified. Comparing the host galaxy offset measurements with other transient classes, both of these studies concluded that FRB locations are statistically distinct from transient classes like long duration GRBs or calcium-rich transients, suggesting that FRBs may originate from unique or multiple progenitor pathways. The use of AO imaging as a viable ground-based alternative to HST is also a key practical takeaway from these studies. Please keep an eye out for both Alex and Michele's talk later today. They might talk about this in more detail today. Modeling hosts surface brightness profile in deep optical and near-infrared imaging of a sample of 37 well-localized FRBs from ASCAP's craft survey, Alexa's recent work found that despite the fact that 86% of host galaxies in this sample have spiral arm features, only 20 to 46% of FRBs are actually associated with the spiral arm statistically. Most FRBs are actually found to trace the smooth stellar light profile rather than being clustered in star-forming regions or active nuclei. Comparing FRB locations to synthetic globular cluster distributions, they found that approximately 10% of FRBs, primarily those at larger galactocentric offsets, are consistent with a globular cluster origin. And these are the ones that have a statistically larger host normalized offset as well. These results actually support the idea that FRBs arise from multiple progenitor channels. The majority likely stem from young magnetars formed via core collapse supernovae, and a smaller subset may originate from these delayed formation channels. But they also point out that there's no clear preference for high star formation efficiency for the formation of FRB sources. Alexa is going to talk about this in more detail in her talk later in the session today. To really get to the question of formation channels, any empirical constraints on the age of the FRB source could be tremendously helpful. So far, the FRB community has compiled a sample of about 50 FRBs with measured star formation histories through their detailed spectral energy distribution modeling. The star formation history encodes the degree of active global star formation in the host galaxy, which could serve as a proxy for the progenitor age. One widely used method of probabilistically quantifying the range of ages of progenitors is through the transient's delay time distribution, which quantifies the probability of occurrence of the transient after a certain delay time since the birth of its progenitor star. Conventionally, the transient rates are modeled as a convolution of the delay time distribution with the star formation history of the galaxies. Therefore, given the transient rates and FRB host galaxy star formation histories, we should in principle be able to fit for its delay time distribution. Several works in the literature have already used this method to measure delay time distributions of various transient classes. As an example, Zapatas et al. Used exponential star formation histories with a Gaussian delay time distribution model to find a maximum delay time of about 250 megayears when core collapse supernovae with time scales greater than 50 megayear involves some sort of a binary evolution. Similarly, Zeman et al. Used a sample of 68 host galaxies of short duration GRBs to fit for the parallel index of the delay time distribution, which was about -2, and minimum delay times of about 100 megayears. Friendlich et al. Repeated the same exercise for type 1 supernovae to fit for an exponential star formation history together with the parallel delay time distribution. So this is a fairly widely used method for measuring the delay time distribution of transients. So using a sample of about 30 FRB host galaxies localized by DSA 110, we tested several delay time distribution models. Unfortunately, we are still in a low number regime and there's no clear preference for one model over the other. Furthermore, there are also several challenges or limitations of using such global star formation histories for inference of the delay time distribution. The global star formation history actually represents the characteristic stellar population age, which need not always be representative of the local source environment. As an example, FRB 2018-0916b was localized to a spiral Milky Way type galaxy with characteristic stellar population age of several gigayears. However, the source itself was approximately coincident with a star forming region with a characteristic age of less than 100 megayears. Therefore, if the dominant formation channel involves a young or very old stellar progenitor, then in that case, the global star formation history could lead to biased inferences. These limitations advocate for using the resolved star formation histories in the local environment of FRB sources. Several of us in the room here have ongoing spatially resolved spectroscopy programs on meter class telescopes such as Keck with, broadly speaking, twofold goals. First is to measure the local star formation histories to put constraints on the source ages. And the second is to quantify the host dispersion measure contributions along the FRB site line, which may be correlated with young progenitors. Specifically, a uniformly selected sample in the local universe with sensitive enough observations to target, let's say, H-alpha luminosity comparable to that of Milky Way star formation surface density should be sufficient for an unbiased inference. Here for the DSA-110 team, the data for our program PI'd by Stella is already coming in. And as an example here, I'm showing the imaging centered on H-alpha wavelength for two of the nearest FRBs in our sample, including Mark and Mizu. For FRB Mark, for example, we are able to associate the localization region or the FRB itself with that of this nearest star-forming region in its host galaxy. Overall, I think we're all very excited about what we can learn from such observations for both FRB source formation channels as well as host DM contributions. Millisecond localizations with the newly operational CHIME outrigger array have now opened a transformative path for understanding FRBs, especially the majority that appear as non-repeaters. By routinely achieving localization precisions of the order of tens of milliseconds, corresponding to physical scales of about 10 parsecs for some of the nearest sources, CHIME outriggers can now make it possible to directly probe the local environments of FRBs that are one-offs, something that was previously limited only to a handful of bright repeaters. In this context, CHIME FRB collaboration presented the discovery and precise localization of FRB 2025-0316A, a bright and nearby about 40 megaparsecs, one-off FRB that was localized to this 13 parsec region, marking the first such result with the full outrigger array. The burst lies at an offset of about 200 parsecs from the nearest star-forming H2 region in its host galaxy, and JWST observations revealed this fainter source in near-infrared, and the properties of this one are actually consistent with a massive main sequence star or an RGB clump, and inconsistent with that of a globular cluster, supernova remnant, pulsar wind nebula, or a magnetar. As one of the most precisely localized non-repeating FRBs to date, this FRB demonstrates the power of millisecond localizations for mapping the diversity of FRB host galaxy environments and constraining the nature of their origins. Lastly, I just want to emphasize that the characterization of FRB host galaxy environments are not only important for tackling the formation channel question. It is also very important prerequisite for precision cosmology, using FRBs as probes of large-scale structure and baryons. Specifically, the host DM contributions are degenerate with the cosmic contribution and can serve as a systematic in DMZ analysis, as well as contribute to short noise in cross-correlation studies, thus limiting our ability to probe small scales with FRBs. Therefore, any knowledge of the FRB source formation channels and expected local DM contributions could serve as an important missing piece of the puzzle for doing precision cosmology using FRBs. Finally, to conclude, I would say since the discovery of the first FRB, the Lorimer burst, we've all come a long way from VLBI millisecond localizations of FRBs on account of their repetition to arcsecond scale localizations of all FRBs including non-repeaters upon discovery to VLBI millisecond localizations of all FRBs out there. FRB host galaxy studies support multiple formation channels so far, ranging from young stellar populations in dwarf and spiral galaxies to old stellar populations in globular clusters and elliptical galaxies. High-resolution imaging studies of FRB host galaxies do not indicate a preference for spiral arm features or high star formation efficiencies. Going forward, the only practical way of constraining the progenitor age would be through spatially resolved spectroscopy of FRB sources in nearby galaxies, localized to millisecond precisions. Studies of FRB local environments are also of prime importance for the era of precision cosmology using FRBs to put better constraints on host galaxy systematics on those analyses. With that, I'd like to stop and thank you all and take any more questions that you may have. Thank you so much.
Hey, Kritti. This is Siggy Pleuris from the University of Amsterdam. Nice overview talk. My question was about FRBs that are in globular cluster or satellite galaxy, where the global host properties don't represent the local environment of the FRBs, and if you had any thoughts on how to handle those in the future.
I really think I have a lot of hope with what we can do with CHIME outriggers and milli-oxygen localizations. I think the best way to go about it is by looking at spatial offset distributions corrected for selection effects. And I think Alexa's going to talk about this later today as well. So she compared the host galaxy normalized offsets for FRBs and separated them out into multiple populations based on their galaxy light profiles. So I think to really distinguish those cases, we should be looking at offsets and pick out FRBs that have relatively larger offsets. And other than that, I think building up a larger sample of nearby FRBs and doing a spatially resolved spectroscopy program would be very helpful, as I mentioned in the talk as well. So we already have it ongoing with several of us. I think Sunil also has an ongoing program for the same. And repeating the same exercise for, say, redshift less than 0.05 FRBs would be very helpful. Yeah, go ahead, Sunil.
Hey, great talk as usual. This is Sunil from Northwestern and U Chicago. I was just wondering if anyone has done like the calculation for checking if radio flares from red dwarfs could be producing FRBs, because all the distributions of the radial distributions of FRBs with respect to their host galaxies seem to be generally just tracing stellar mass and not particularly star formation. So I was just wondering if that channel of FRB progenitor has been looked into.
I don't think so. So if I recall it correctly from Alex Mannings and Michele Woodland's work, and then later by Alex as well, I think most of the times the comparisons are done with more of the common transient classes. So red dwarfs have not really been considered in such comparisons, but I think it's a good question. We should be including that as well going forward.
I'll just briefly say for those online, we find FRBs in diverse environments. Either this implies the progenitor is common, that doesn't care where it comes from, or they don't really select for distinct environments. For this project in particular, I was interested in zooming in on the local and thinking about using the locations of the FRBs within their galaxies to understand the underlying progenitor populations. And then we'll step smaller. Okay, so the literature gives support for multiple formation channels for FRBs with both prompt and delayed channels. So the prompt channel is largely an FRB that would come from a massive star going core collapse supernova to leave behind a magnetar that at some point gives off an FRB. In this scenario, you would expect to see most FRBs in areas of recent star formation. You don't have a lot of time for the massive star's lifetime for that remnants to travel very far. However, in a more delayed case, such as a compact object merger or accretion-induced collapse of a white dwarf, you would have a weaker correlation with star formation or even presence on the stellar disk. So for this project, I decided to test the spatial correlation of known FRBs against several different models. So the first one was a smooth stellar light profile. So this is a parametric fit to the galaxies using a Sirota profile. The second one is a model of the residual substructure. So largely this is tracing the spiral arms. So this also comes from GalFit. So the process is you fit these smooth profiles to the galaxies, subtract off that profile, you get the residual. And lastly, motivated by the one FRB we know comes from a globular cluster, I create synthetic distributions of globular clusters. The reason for this is we can only observationally see globular clusters out to a redshift of about 0.1, and the large majority of the sample is beyond that. So instead, I create these synthetic distributions using sort of two formulas for how they are distributed about their galaxies, what I call GC ellipsoidal and GC spherical. In general, these are about 4 times more extended than the observed stellar light distribution. Okay, so those are the models. Next is the sample. So I compile a sample of 37 FRBs, 34 of them detected by the craft team. And these all have optical R-band and infrared K-band imaging. So the majority of the data for this program come from the FRB large program and the Very Large Telescope that we had, about 100 some hours of observing time, which is really awesome. And this is supplemented by observing from several other facilities as well, which I've listed along with the PIs there. Okay, so we have the models, we have the FRBs now to test them. So to do this, my collaborator Alan Deller and I created this model likelihood testing code called CoFlash. Correlating FRB location and substructure of hosts is what that acronym stands for. This is publicly available on GitHub. It's very flexible. If you're interested in using CoFlash, come talk to me. So ultimately, this is a statistical framework to get at the question, which model is the FRB most likely to have been drawn from? So the way this works is you have the 4 models, normalize them to essentially create probability density functions of their spatial distributions, involve that with the FRB localization, which we assume is a 2D Gaussian, and then measure the model likelihood. So each of the 4 models for every FRB will have a value of the likelihood. The largest one is the most consistent model for that FRB, which I term the preferred model. So what does this look like? So here's a summary bar chart of the 4 models, number of FRBs, which I've split both into the model preferences and the preferences that are statistically significant. So what you can see here is the majority of FRBs do prefer the smooth stellar light profile. It has both the largest number of raw model preferences, but also statistically significant preferences. The residual model, 9 out of the 37 FRBs select the residual, but only a small fraction, 3 out of 37, do so significantly. But it's a little bit more complicated than that, because it turns out that at a redshift of about 0.15 and above, we are insensitive to spiral structure. So for a more apt comparison, when we limit to this redshift range and compare the numbers again, you can see the residual fraction is a lot higher. So this is where the 20 to 46% number comes from of FRBs that are statistically associated to spiral arms. It is interesting to note that when you compare similar redshifts where you see core collapse supernovae in their hosts, about 88% of those occur on spiral arms. We look into a bunch of things in the paper of what could be causing this, and ultimately can't really explain why so many more FRBs are not occurring on spiral arms compared to core collapse supernovae. One thing I should note is that the localization sizes of FRBs are still a lot larger than core collapse, so that could be one of the reasons going on there. I now want to highlight the GC results. So this one that I've highlighted here, the single statistically significant GC ellipsoidal FRB, is the known GC FRB 2021-20E in the outskirts of M81. So this was really reassuring that CoFlash got it right, and it was cool to see that that selection was statistically significant. But if you notice in the spherical bin, there are 2 FRBs there. So these are 220105A, which is a craft FRB, and 240209A, also known as R155 from CHIME. And these have similar statistical significance to the known GC FRB. So this demonstrates that more than one currently known FRB plausibly originates in a globular cluster, showing that not every FRB is associated with the recent star formation, though there is no statistical evidence for every FRB to occur in a globular cluster, just probably more than one. I go into in the paper quite a bit a lot of things that can be driving the model preferences. I don't have time to get into all the considerations, but one I wanted to highlight here is the galactocentric offset, which Kritti also mentioned in her overview talk. So what this is showing is all of the FRBs sort of clumped into two populations. So the disk in this pink color are the FRBs that prefer the profile and residual, and then I've clumped the two GC models into one there. And then I've drawn these concentric circles of effective radius, so that's the characteristic size of the galaxy. So one way you can interpret this plot is sort of a normalized view of where all these FRBs are occurring in their hosts. And so what you can see is that the majority are sitting within this one effective radius boundary, demonstrating that FRBs tend to sit right on top of their galaxies, with only a few found at higher offsets. There is a clear delineation between these two populations beyond about the 2 effective radii contour. Only GC models are preferred, and beyond that at about 4 or so is when they're always statistically significant, though there's just 2, so kind of hard to say if the boundary is actually a 4 or not. So yeah, what I want to take away from this is that the CoFlash framework provides a novel test of globular cluster origins solely from FRB or imaging of the host and the localization. And this is really key for FRBs beyond redshift to 0.1, for which it will be extremely difficult, if not impossible, to ever observationally confirm the globular cluster origin. Okay, so what does this all mean? So this work demonstrates that multiple progenitor channels are required to explain the FRB population. So on the prompt channel side, we find that the majority of FRBs are associated with the stellar disk. It's interesting to note that star formation occurs all throughout galaxies, about 50% on spiral arms, 50% off spiral arms. I thought there would be a lot more going on in the spiral arms than that, but that's what the literature shows. So the takeaway from this is that even though we're only seeing a small fraction of FRBs on arms, they are still consistent with a massive star progenitor, either formed directly on the arms, so these would be the ones preferring the residual, or formed in situ. These would be the profile preferences. However, it's important to note that the infrequency of spiral arm associations can imply that FRBs might not trace areas of high massive star formation efficiency. And when I say massive, I mean like O-type stars. B-type stars are still roughly consistent with their positions. For the delayed side, I find that only a minority of FRBs are consistent with the more extended spatial distribution of globular clusters, with more than one currently known FRB plausibly occurring in a globular cluster, requiring a delayed or dynamical formation channel. We estimate up to 20% could form through these channels. It's a very sort of pessimistic assumption there. I think the true number is a lot lower. But even this high upper limit of 20% is still consistent with global host demographics and magnetar rates in globular clusters. So with that, here is my summary. I want to highlight also, if you are interested in this work, it is on arXiv. There's a lot more there, and I will take questions. Thank you.
Thanks, Alexa, for that talk. So since we are not able to use the catch box, maybe you can repeat the questions from the audience. Okay. Yeah.
2 questions on offsets. So for for the Galaxies, we have a sense of what's their vertical offset from the thickness. So for the FRBs that come from edge-on galaxies, do we have a vertical offset distribution for those FRBs? The second of the question is, for these FRBs that arise from spiral galaxies, do you have an offset distribution for the distance to the closest spiral?
All right, so for online, the 2 questions were the offset from the stellar disk of the FRBs, and then the second question is the measurement distance from the spiral arm. For that second one, wait a couple minutes for Alex Manning's talk, and that will be exactly answered there. So for the first one, I have, I think, 2 edge-on galaxies in my sample. I don't quantify distance from the disk, but they are largely consistent with being in the plane, so not high up in the halo if this is the galaxy. We don't have this situation, they're more like this.
Thank you.
Yeah.
Yeah, there was a question online. Yeah, Sharma, you could agree.
Shami, if you want to go ahead and unmute.
Yeah, it's not, well, I'll ask it anyway. It seems like your positional uncertainties for the FRB localizations contribute to the models not being particularly sensitive in terms of choices. So presumably in this epoch of milliarc second or 10 milliarc second localizations, they'll get a lot more sensitive. Do you have a sense for how many you would need at, let's say, 10 milliarc second localizations before you'd be very confident in I'm seeing spiral arms or not seeing spiral arms?
Yes, that's a great question. And that is something that I do consider in the paper. So this plot here I didn't have time to get into is essentially what's the like projected size the FRB takes up on the spiral, not the spiral, just on any galaxy. And you're exactly right that even with the selection cuts I've made to have localizations that are smaller than the galaxy size, there's still there's a bit of uncertainty there. So one of the things to highlight from this plot is that the residual panel in particular, you need a localization that is less than half of the galaxy size to tie back to a spiral arm, and even smaller than that for a statistically significant preference. So yes, this is something that, you know, the results are dependent on the localization size. I don't have a number of how many more we would need to better constrain the fraction that are coming from arms, but definitely as many, we should totally keep finding more FRBs and high, good precision localizations that will get at this question.
We unfortunately don't have any more time for questions, but please feel free to reach out to Alexa on Slack or during coffee and lunch breaks. Let's thank Alexandra. Okay, so next up we have Alexandra Mannings, who is going to talk about FRB burst properties and local environments. So you'll have 12 minutes to present. Take it away.
Okay, hello. I'm Alexandra Mannings. I just finished my PhD at UC Santa Cruz. Thank you. Today, I want to talk about kind of building a total picture between burst characteristics and the characteristics of the local environments of fast radio bursts. So a lot of the data and measurements that I'm using are from the CRAFT collaboration, with some from other observatories and experiments as well. And of course, largely supported by F4, Fast and Fortunate FRB follow-up, and lots of work from the people listed here. So I guess just starting with the question, are there any notable connections between burst and local environment characteristics, just broadly? But then from there, thinking, well, what might we expect? So starting from a place of some hypotheses or questions. So the first question, for example, could be, do older FRB sources produce intrinsically broader bursts? Or are they associated with highly scattered bursts? So some sort of question about the age or delay time of the progenitor. Another question might be, does the density of stars affect the density of the circumburst media? So does the amount of stars or stellar mass in that local environment affect some other burst properties or characteristics that we see, like dispersion measure, scattering, something like this? And then maybe another question is on what physical scales might these connections exist? So a lot of our localizations can maybe probe to like parsec scales, but for the most part, we're kind of working on half kiloparsec scales. So if there are some sort of connections to like smaller scale variations or characteristics of the local environment, are we still sensitive to that with the localization precision that we currently have? So, one, I guess, example of this kind of marriage of burst properties and local environment properties that really help to illuminate the possible origins of an FRB is in the case of 2012 1102A, where we saw that it was located within the star-forming region of its galaxy, the star-forming dwarf galaxy, and then also through the measurement of this very, very high rotation measure, as well as some other burst properties, we kind of hone in on this story of an extreme magneto-ionic environment around this FRB, or that this source is embedded within. So these kind of two approaches to answering this question can kind of help us build a more holistic picture of what might be going on. And then we also see this with other high rotation measures as well. There was just an ATEL put out by Kraft for a very high rotation measure burst, and looking at the combination of what the host galaxy or local environment characteristics are with the burst characteristics can help us kind of get to an answer of what's going on. So returning again to our questions of what we might expect, I want to focus first on the first question: do older FRBs, older FRB sources produce intrinsically broader bursts? But really what I'm trying to say is then how do we determine this age? How can we use locations of the FRBs within their hosts to understand what their age or delay times might be? So first, I'll just start off by talking about the sample that we use in this study. Some of the requirements were just really bursts with high resolution imaging. So this includes ground-based AO imaging as well as HST. And then all of these have been presented in previous studies, many of which were in the ICS sample presented in Shannon et al. 2024, including some others previously published elsewhere. And we required, well, I guess we didn't require, but we have information on dispersion measure, rotation measure, scattering, fluence, all of these other burst properties and characteristics for most of the FRBs in this sample as well. Okay, so kind of referencing this paper, I think Alexa also referenced this paper. It's very popular with our group. This Aramayan look at the distance of these different types of supernovae, so type 2, type 1 BC supernovae from this shock front in the spiral arms, where we're assuming that at this shock front there is star formation happening from this like compression of the material, creating these dense regions of star formation. And from there, after these sources are born, they drift some amount until this supernova goes off or something like this. So what they do is they measure the distance between the, or from the brightest pixel, or like the peak in the brightness profile of this arm to the location of the supernova. And they're all normalized by the arm width. So these are normalized distances. Our version is a little more simplified. We didn't do brightness profiles of the arms. We really just say, okay, where is a spiral arm and what is the physical distance in kiloparsecs to this nearest part? It can be an edge, it can be some central part, just whatever location or pixel is closest to the location of our FRB. So we start off with residual images. I'm using 2018-09 16B as an example. And the purple circle or little donut shape is the FRB location. The white is the spiral arms that have been pulled out or highlighted in this residual image where the smooth light has been subtracted away. And then the identified spiral arms are the regions that now have this black hatched kind of texture over it. I did a bad job at choosing what color should be on here, but now the spiral arms are kind of blocked out with this black. And again, showing the FRB location with that purple circle. And the R-min is what we decided to call this. The spiral offset is about 0.008 kiloparsecs between the FRB location and the nearest part of the spiral arm. As I think Kritti mentioned, the distance to the brightest pixel or brightest region in that star-forming knot that this FRB is close to is about 250 parsecs. So this makes sense, I think, in the context of that. Okay. So then we also want to compare this or understand what the distribution would be if we're thinking about spiral arms or a disk distribution or a spherical globular cluster distribution to understand if these FRB spiral offsets show any similarities to the spiral offsets of other kinds of models. So again, going back to our identified spiral arms, so this is our true spiral arm locations in the black. Then we grow that a bit to determine or define some sort of spiral arm model. So that's what's shown in the green. So the green not only includes all of the black pixels and points, it also goes a little bit beyond that, you know, maybe to highlight regions of the spiral arms that we weren't sensitive enough to pick up in the residual images or regions that our initial selection didn't include. So we randomly generate points from this spiral distribution and then calculate our minimum distance to the true spiral distribution. Then we also determine a disk model and a spherical globular cluster model. Again, drawing random points using the smooth light distributions that were, or specifically for the disk model, using the smooth light distribution that was determined by Galfit, and using this to then create a PDF from which we can draw random points. And again, measuring the minimum distance between these random points and our spiral arms. And then the same for a spherical globular cluster model. And usually, or in many cases, the globular cluster model does extend beyond what we see here in the disk. But for 1809 16B, it's a bit more concentrated towards the center. Okay. So this is what we find. We show the FRB distribution, a CDF in black, and then we're also comparing against some measurements, similar measurements that we found in a paper from the 90s, 1994, which did a very similar thing that we did, just looking at the physical distance between the location of type 2 and type 1a supernovae to the nearest spiral arm. So we show that in this kind of pink and orange colors, and then showing our smooth distributions from the models. And in general, or in this current iteration, we're able to reject the null hypothesis that FRBs are drawn from the same distributions as the spiral, the random, so just random points across the image, and disk distributions and models, but we don't or are unable to reject it for the supernovae of either type 1a or type 2, or the spherical globular cluster distributions. Okay, great. So then using this now age kind of measurement, looking at this distance from the spiral arm, we asked the question, does this distance correlate with burst intrinsic width? So we're looking at the width that encompasses 95% of the fluence of the burst and our R-min or spiral offset, and we don't find any notable or strong correlation between the two at this point. Okay, and ending with our second question, does the density of stars affect the density of circumburst media? Or in other words, like, are there environmental effects on these burst properties? And so we take a look at the stellar mass surface density. So that's in terms of stellar mass per kiloparsec squared against the 1 gigahertz scattering time, and also again that burst width. And we find a moderate but statistically insignificant correlation between the scattering time and stellar mass surface density. And then we find no notable correlation between stellar mass surface density and the burst width. We also look at fluence against these different measurements, the stellar mass surface density and minimum offset from spiral arms, and don't find anything there either. So no strong correlations. Okay, and my summary. So there is this possibility of using this minimum spiral offset as a way to understand FRB progenitor or source drifts and ages. And then in our exploration of looking for correlations between burst properties and local environment properties, we do not find any strong correlations, but we should keep looking. Thank you.
Thanks, Alexandra. Questions? Oh, yes, Stella.
Really nice talk. I was wondering, also planning to look at the correlations between burst properties and, say, star formation rate, and also post-DF.
So we did look at burst properties, and then we looked at scattering and star formation rate. And didn't find anything. Looked at star formation rate like globally, presently or current star formation rate, as well as in the past like 100 mega years or something, and didn't find anything there either. Yeah. Oh, and hostium. Yes, we did do that. And didn't anything. Sorry. But that doesn't mean it's not there. Just that, yeah, it wasn't present here.
Okay, are there any online questions? Okay, so let's thanks Alexandra again. For our next talk, we'll have Hugh Roxburgh, who is going to discuss if most FRB hosts are disturbed, which is going to be on Zoom.
Hello, can everyone hear me? I can just share my screen if that's possible, or if that's not possible.
Yeah, it should be. I'll just stop sharing.
Cool. Apparently I've had to request to be able to share my screen.
Yep, should be good now.
Sweet, cheers, thank you. Cool, can everyone see my screen?
Yeah, I'll just full screen it. I've done this so many times.
I misguided you.
There's not. I see. Yeah, should be good.
Yeah, go ahead.
Go for it.
Cool, cheers. Okay, hey everybody, my name is Hugh and I'm a second year PhD student here at Curtin University in Perth, Australia. So I currently have a perfect 12-hour offset to time, which is amazing. Now, just now, we've kind of heard a lot more in your morning about the optical properties of the host galaxies of FRBs. But today I'm going to delve back to radio wavelengths and cover the distribution of H1 emission in these galaxies in order to answer this question: are most FRB host galaxies disturbed? Now, for those who aren't super familiar with H1, this is the signal that is emitted by atomic hydrogen gas, essentially large groups of neutral hydrogen atoms that are all clumped together. This emission arises due to quantum mechanics, where the single bound electron orbiting the hydrogen nucleus prefers to exist in one spin state over the other. And as a result, there's this energy difference between the level of these two states. And so this atomic hydrogen can be excited when it absorbs some energy and then spontaneously relaxes back down to its ground state and re-emits that energy as radio light with a wavelength of 21 centimeters. Now, H1 is an incredibly useful tool for host galaxy, or just for galaxy studies in general. It is generally the most abundant gas in galaxies, and as you can see here, it often extends far beyond the optical disk. And so, as a result, H1 emission encodes a whole bunch of information about the large-scale kinematics of galaxies, and is far more sensitive to perturbative dynamics that may be subtly affecting their evolution. So this can include any internal outflow mechanisms, such as those that are driven by AGN, or any external tidal disturbances from gravitational interactions with nearby galaxies or gas clouds. Now, as has kind of been covered already today, FRB hosts generally are star-forming galaxies for the most part, and so we do expect that this is a good thing because we expect to see H1 emission coming from star-forming galaxies, because atomic hydrogen gas is the fundamental fuel for star formation. So if you have these high star formation rates, you need a lot of fuel, and therefore you are likely to have a large gas reservoir that's able to emit in H1 as well. And as a result, we are able to probe the underlying dynamics of FRB host galaxies using this alternative regime as well. Now, prior to my work, only 5 FRB host galaxies had been observed in H1, but there was an interesting trend that emerged. All 5 of those host galaxies exhibit a highly disturbed H1 profile, all of which have been attributed to recent merger activity. So, for example, here is the H1 spectrum of the host galaxy of FRB 2018-1030A, which shows this characteristic kind of double horn shape that we expect, but also has a significant asymmetry either side of the middle. And this is a hallmark sign of disturbance in these types of profiles. Now, here's another example where we have a contour plot that shows the spatial distribution of H1 emission. And for those unfamiliar, we call these intensity maps. And the more central your contours are, the stronger the emission. What we can see here is that there is a tidal tail feature, as we call it, which is a bunch of gas mass that has been stripped or ejected from the main gas clouds surrounding the galaxy. And in this paper, it was concluded that this is most likely caused by gravitational interaction between the host at the top and this kind of sliver of a satellite mass below. Now, this 5-to-0 disturbed to undisturbed ratio is an interesting observation. Merger activity has been shown to potentially stimulate or amplify star formation. And so if we're seeing that most or even all of our FRB hosts are disturbed in this way, that provides further evidence that might support these fast channel progenitor theories associated with star formation. Of course, I've talked about 5 examples, so we're definitely in the regime of low number statistics, and we want to expand that sample as much as possible and increase the number of FRB host galaxies observed in H1. And that brings me to my work, which aims to do just that in order to shed more light on this kind of emerging trend of disturbance, and also to simply look for any interesting characteristics in the H1 derived properties of FRB host galaxies. So where do we start? Well, we need a sample. And for us, we determine the FRBs to be included in the study based on 2 criteria. Firstly, we require that the FRBs have robust host associations, which we define as having path probabilities greater than 0.9. Secondly, we require that the host redshift is no greater than 0.1. And this is due to the fact that the H1 signal is inherently pretty faint. And so the upper redshift limit for secure detection is currently around 0.1 with current generation telescopes. Thus, we are left with this sample here of 14 new targets, which nearly quadruples the previous sample size. Now, the group in the first section here are targets that we put in dedicated observation proposals for last year with the GMRT in India, FAST in China, and MeerTRAP in South Africa. And those final 3 at the bottom are CHIME targets, which were reported earlier in the year. And so that was well after proposal deadlines, but they had archival data sets that were available that we could just access online. So what do we find? Well, here are all the spectra from these targets. And you'll see that 13 out of 14 of them are indeed emitting in H1. The single non-detection that we have happens to be the one galaxy in the study that, according to previous optical studies, is transitioning towards quiescence. So it makes sense that it has a much smaller gas reservoir and this is not exhibiting a strong H1 signal. Now, for the rest of them, how do we determine whether or not they're disturbed? Well, we can do this in two ways. So firstly, we can use our eyes. Does the spectrum look funny? Does the intensity map show significant deviations from a smooth disk? This is pretty self-explanatory, but is also quite important, as I'll get to in a moment. However, we also want to be able to quantitatively compare with the background population of random local universe galaxies, and so we also do utilize common metrics to describe the level of disturbance in these profiles. Now, due to time constraints, I won't really go over the metrics in detail, and I won't talk about the thresholds above which we consider a profile to be disturbed. All you need to know is that there are a lot of them that we use, and they're all kind of tied to the asymmetry of emission about some central rotation axis. So for example, in one dimensions, you can set the center to be this certain channel, and then you measure either half of it, for example. In two dimensions, you can compare each pixel and then rotate the whole intensity map by 180 degrees and do some comparison. And then you can also extend this into three dimensions by taking a centroid in space and also a central channel and rotating every like voxel around in our data cubes. So what do we find? Overall, of the 13 detections that we have in H1, we find that 6 of them are indeed disturbed. We can see in the top left, there's a pretty strong tidal tail, as I showed earlier. And in the bottom middle one, we have an FRB host that's going through a major merger with a much, much larger galaxy. And so their H1 clouds are kind of overlapping. Now, the bottom two corners are two of the archival data sets. So we don't have spatial H1 information, but their spectra qualify them to be considered disturbed based on our metrics. And if you look at optical survey imaging, they potentially allude to some level of disturbance, but obviously that's very speculatory. We have to get some more H1 information to fully figure this out. Now, you might be wondering how we consider the top right one to be disturbed. And this is one of those cases where the metrics just simply aren't enough, and you kind of need to use your eyes to be able to figure this out. When you look at just the spectrum and just the intensity map and you take them at face value, they appear mostly as we expect for a rotating disk. However, this kind of slight bumpiness along the northern edge actually turns out to be a pretty significant gaseous extension along the northern side, which was only revealed when we went deeper with this individual channel map inspection. And this is likely caused by some nearby dwarf galaxy churning up the gas along the side. But as we don't have redshift information for like all the potential neighbors, we can't like rule anything out for certain. Now, importantly, we do find that 4 of our targets are undisturbed, with symmetric spectra and spatial profiles that follow a smooth rotating disk. Sorry, and just to reiterate, such examples have not been demonstrated so far in FRB hosts, so it's kind of important to be able to see that these things definitely can be settled. We also do have 3 other targets which are either too low signal to noise or too low resolution to be sure about, and so we exclude them from the rest of our analysis. Now, where does that leave the question? Are most FRB hosts disturbed? Well, as with a lot of science, it's complicated. Prior to this work, we had the pretty unambiguous ratio of 5 to 0, but now the ratio of ones that we're confident about is 11 to 4. And so the question that I'm sure many of you are wondering, what ratio do we expect what ratio do we expect the trend to follow if the trend isn't real, if that makes sense? And this isn't very easy to answer. Many previous studies have used the metrics that I briefly talked about to measure disturbance in different samples, with some looking at isolated galaxies and some at galaxies in groups, and a bunch of them choosing a whole bunch of different...
2 more minutes, Hugh. Sorry to disturb.
No, you're good. Thank you. Awesome. And many of them are choosing completely different thresholds above which the profile is considered asymmetric. So based on those quantifications, those studies have found anywhere between 10 and 40% of galaxies show disturbance. However, because we've investigated our sample into a lot more depth by looking at those individual channel maps and being a bit more precise, we kind of have to do something a bit different. And so based on that literature rabbit hole, you're just going to kind of have to trust me on that. And to account for the extra depth that we've gone into for these targets, we roughly estimate that a 1-to-1 disturbed to settled ratio is a conservative estimate for the expected ratio of FRB hosts. So if we expect a ratio of 1-to-1 and we observe a ratio of 11 to 4, then we clearly still have an excess of disturbance going on here. If we assume Poisson error and perform a significance test to reject the null hypothesis that the FRB hosts should follow this 1-to-1 ratio, we find a p-value of 0.065. So this is not quite at the level of significance that we tend to require, but it's really, really close. And unfortunately, what that means is that we need more data to be able to actually fully rule anything out. That's also science. We love it. Now, briefly at the end of this talk, I'll just highlight a few of the H1 properties of FRB hosts and point out anything interesting. So this plot here looks at H1 mass on the x-axis and star formation rate on the y-axis, and our FRB hosts are overlaid in red and blue on the X-gas sample. Now, on the whole, we can see that FRB hosts are generally pretty massive in H1 because they're on the right side of this plot. And this is very much in line with what we've heard in the past in terms of having somewhat like larger stellar masses and a deficit of lower stellar masses. Now, I've also separated these hosts into red for non-repeating hosts and blue for repeating FRB hosts, apparent non-repeating hosts. And by eye, and also if I put some circles around some things, you can potentially see a distinction between the masses where repeating hosts are falling to slightly lower masses. Now, you won't be surprised that this distinction is not very significant. It's not a statistically significant thing, but it is at least the fourth case in the literature where we were seeing a potential preference towards slightly lower mass galaxies for the hosts of repeaters. And I should note that none of our repeaters hosts are included in those previous samples either. So this is definitely something to keep an eye out on, but so far not statistically significant. Now, I'm probably running out of time. This is kind of a plot that I was going to show that basically just suggests that beyond what I've just shown, the H1 properties of FRB hosts are very varied. We span a whole range in this domain and a bunch of other comparisons that I could make. So much like the optical, FRB hosts in H1 are also widely varied. And yeah, I'll just leave you with my summary slide. And the paper is going to be submitted tomorrow is the plan, maybe Thursday. We'll see. But yeah, thank you very much. Appreciate it.
Thanks, Hugh. Do we have any questions? Adam?
Thanks for the talk. I guess you'll like the question. You done any follow up to see if any of these hosts are identified in the Galaxy groups or other environments? We're starting to see a lot some other FRB hosts that are in these multiple Galaxy systems.
So Hugh, this is a question by Adam Landman, who's a postdoc at MIT. The question is whether you have done any follow up to see if these disturbed hosts are in Galaxy groups, because we are finding more and more FRBs which tend to occur in Galaxy groups.
Yeah, great question. So because of these, particularly for the observations that we have with GMRT and MeerTRAP, we can look much wider in the field at to see if they're in H1 rich groups, and we find that a lot of them are in groups that are in regions where they're within 2-3 megaparsecs of other H1 detections as well. So we didn't see a significant there was some disturbed galaxies that are isolated apparently in both optical and H1 detections, but there are some that are very nearby, and there are also some of the settled galaxies that we've also seen, which are in really close to other galaxies, but they appear to be settled. So there wasn't a huge trend, but we did observe that cutoff. Yeah.
Okay, we probably go to online question. Yeah.
Yes, you know.
Oh, Sunil, can you unmute and ask your question?
Oh, yes. Great talk, Hugh. I was just wondering if you had the resources and the time, what kind of galaxies would you choose to build your field population with to do this comparison in the future?
So do you mean as in if you to compare with random galaxies in the not
Yeah.
necessarily yeah.
Yeah.
So I guess the idea is that we kind of want to build our comparison population with things that are similar in mass and star formation rate. So we tend to want to look at things that are massive and probably massive spirals that have gas in them. A lot of those previous works, for example, if I just skip back to this slide here, where you can see LVHIS and halo gas, those were populations which were notably in isolated fields. And so it's kind of tricky with so many different ways of quantifying this asymmetry and this disturbance to pick out certain populations to compare with, but we'd really like ones that are kind of representative of local spirals, if that makes sense. Kind of more along the lines of these gray dots in the X-gas sample, which are likely to be more gaseous because they are detected in H1, if that makes sense.
Thank you.
Okay, we don't have time for more questions, but please feel free to ask your questions.
Yes, ask on the Slack,
So
please.
let's
Cheers,
thank
thank
Hugh
you.
again. And next up, we have a lightning talk by Ben Stappers about hunting FRBs with MeerTRAP. And just a quick reminder again for people asking questions to introduce yourself first. And you can take it away, Ben.
Right. Hello. Thanks, everybody, for attending and giving me the chance to give a talk today. Sorry, just trying to find a way to so that you can actually start to see me. Yes, thanks very much for making this possible and for allowing me to give a talk to quickly summarize 5 years of MeerTRAP. You heard a little bit about this already from Kaustub yesterday. So it's a project that runs on the MeerKAT telescope. It does fully commensal observing. We also have this opportunity to do simultaneous optical observations with Meerlicht as well. And we've been running approximately 5 years now. This is clock time, not wall time. So it's probably closer to 2 to 2.5 years of on-sky time. Of course, these things aren't possible without a large group of collaborators who have supported us over the years, and we're very grateful for all of the work that these people have put in the past and hopefully in the future as well. Also, thanks to Sirota for their support of our observing campaigns, and also to the MeerKAT observers who have been graciously allowing us to be commensal with their observations, and also to the Max Planck Institute for Radio Astronomy for providing some of the hardware that we use. So wanted to just give you a summary of where we're at after this amount of time. So we have a sample of 78 FRBs approximately that we found so far. And what you can see here in these graphs is the fact that we actually do 2 experiments in one, in a sense. So we have the capability of observing in the coherent beams, which have a sensitivity which is somewhat higher than those in the incoherent beams. And so these plots are showing you the FRBs that we found and the distribution as a function of DM. The top left-hand plot is showing all the sample, which has a median DM of around about 870. And then the lower 2 plots are the ones that probably of most interest. These are those on the left are the ones that are detected only in our most sensitive beams, that is the coherent beams, and the median DM of those is around 730. And then in the incoherent beam, we have, which is, like I say, about a factor of a few less sensitive, a median DM, which is actually somewhat higher. And by comparison, the median DMs are around 400 to 500 from a lot of the other experiments. Of these, we have around about 31 voltage dump triggers so far, around about 35 localizations, and so far around 14 of those we have redshifts for. We also observe in multiple frequencies, so about 53 FRBs have been detected in the L band, 24 in the UHF, and still only 1 in the S band so far. And you can see that they have a range of different dispersion measures. We have a nice paper that should be out this week in the archive, led by Ines, which has got 15 of our currently one-off FRBs, 11 localizations, 9 host galaxies, and 6 with redshifts. And so we're with lots of different hosts, which will add to some of the nice talks that we've just been hearing about. We have 2 repeaters so far. You'll hear about one of those in a talk by Kavya a little bit later on today. And the other one is at a DM of around about 830, but a very, very low RM. And we're currently following that up with telescopes at the moment. Given the the time. I'll just also note that there'll be a nice talk by Jun Tian later this week talking about the fact that we found also more than 100 new galactic sources. And so in summary, we found around about more than 75 new FRBs. We probed the high-end region of the DM space. We can localize them using the transient buffer to get the hosts and the redshifts. These high redshift hosts that we hope will be associated with some of these high DM FRBs will tell us something about the origins. And they also pave the way for cosmology. We have around about 2 repeaters, which seems to fit with the statistics so far. We have some nice fields where we've been able to go very, very deep. And so we have a population of FRBs in these fields, which will be interesting to follow up. And I'll stop there. Thank you.
Thanks, Ben. Okay, so Vicky, questions.
Is it surprising that the median are lower in the beams for which there's greater
Okay, Ben, this is a question by Vicky, and the question is it surprising that the median DMs are lower in the beams which have greater sensitivity?
Yeah, it is interesting. We're pondering that ourselves. We're not quite sure we understand that yet, and whether it's a significant difference is the first thing that we need to check on that.
Okay. Is there any online question, Kyle? Is there any online question? No. Okay, so let's move on to our. Okay. They can just unmute. Emmanuel, can you unmute, please?
Yeah, sorry, I'm so sorry. Quick question for you, Ben. Many thanks for the nice talk. It will MeerTRAP, from my understanding, there will be additional dishes added to Meerkat. Will MeerTRAP run in that era?
That's currently under discussion. That's currently under discussion, I guess, is the best way to say that.
Cool, great. Hope so. Thank you.
Okay, let's thank Ben again. And next up, we have Michele Woodland, who is going to talk about highly dispersed FRBs. You'll have 3 minutes.
Yep. I think we need to share this end. Was yeah. What? Oh, yours.
Hi, everyone. My name is Michele Woodland. I just finished up the first year of my PhD at UC Santa Cruz, working with Brian Gainsler. A few people so far have mentioned the AO host work that I've done previously. I'll be talking about none of that. Instead, I'm talking about how the work I'm doing with CHIME now, which is exploring the nature of highly dispersed FRBs. So why we care about high DM FRBs in particular is that they're either high redshift, have complex environments, or intervening material, or both, either of which would be really neat. And so in particular, I've been looking at the high DM FRBs in CHIME Catalog 2, of which there are 42 of them that have extragalactic DMs over 2,000 parsecs per centimeter cubed, so pretty high, the distribution of which can be seen on the plot on the right there. And so typically, they're lower signal to noise than their lower DM burst counterparts. However, analysis can still be done to reveal their origins. And there's just a handful of example waterfall plots at the bottom here. And so there's a lot of different possible explanations for why a burst might have a high DM. For one of which, maybe the most obvious is that it's a high redshift. For example, for reference, a burst with a DM contribution of about 3,000 would say be at a redshift of 3-ish. There could be an intervening galaxy cluster, which is already shown to be possible for a handful of FRBs in Liam Connor's work. H2 regions within the FRB host galaxy can contribute a non-negligible amount to the host DM. as well as just complicated dynamics within the nucleus of the FRB host galaxy. For example, within our Milky Way galaxy, our galactic center magnetar has a DM of almost or over 1,700 just within our own galaxy. So that could contribute non-negligible amounts to the DM as well as there could just be an intervening galaxy or galaxy halo, or perhaps multiple that could also contribute to the DM of the FRB. So now we have all these possible explanations, but how do we actually go about determining the source of high DM? There's a few different things that we can do. For one, we can simulate DM contributions from different sources, for example, which I've already done with galaxy clusters, which can contribute significant amounts on the order of, say, like 2,000 DM units to the FRB DM. We can compare the low DM and high DM populations from CHIME Catalog 2, in particular, looking at statistical differences between some properties. For example, scattering timescale, which I'm shown here on the right, scattering timescale versus DM. And it seems like perhaps for our higher DM bursts, there's as well, they have higher scattering timescales, which makes sense if they're going through more material, they have more opportunities to be scattered, but there's still a very wide distribution within that. And so we can also look at imaging surveys for objects in the FRB line of sight. For example, can we see a galaxy cluster in a survey like decals? That would be a really obvious red herring. And we can also examine the corresponding baseband data for these bursts. For example, the one red dot I have in the plot here, it's a burst FRB 2020-0124D. We do indeed have baseband data for it with CHIME. It has a DM of about 2,700 and a scattering on the order of 60 milliseconds at 400 megahertz. And so now we're going through the process of running all of the CHIME baseband reduction pipelines and haven't found anything of super important so far. But with the CHIME intensity data, we're talking localizations on the order of 10 arc minutes. With baseband, it's on the order of an arc minute. But we're also really excited to see what we can do with CHIME outriggers when we're talking on localizations on the order of arc seconds. So we can really definitively define a host association to see why these bursts might have high DMs. Thanks.
Thanks, Michele. Questions? Online question? Okay, so I can ask a question. So in the population synthesis work done by Caitlin Chen for CHIME FRB Catalog 1, we saw that we predict that most FRBs detected by CHIME would be from less than redshift of 2. So what is, do you have a sense of how many of these FRBs with DM greater than 2,000 would actually be at higher redshifts?
Yeah, so that's obviously a question that we're trying to answer, at least in terms of looking at say if galaxy clusters would be a really obvious option. It seems like maybe only 2 out of the 42 seems like there might be an intervening galaxy cluster. So then maybe most obvious after that is high redshift. For at least this one burst with baseband, we recreated the analysis of Cords et al, where you can use the DM in combination with the scattering to set an upper limit on the redshift, which would be on the order of 2.6 for this burst. So potentially some really high redshifts, but yeah, something we're still looking through.
Okay, great. Okay, let's thank Michele again. Okay, we'll just give a couple minutes for
No, it's good.
Oh, are we not fixing the tempo?
No, for the other slides, everything works. It's just
okay. So next up we have Daniele and Michele, who is going to talk about the sub-second periodicity FRB. You have 3 minutes to present.
Okay, hello everybody. Hope you can hear me all right. So this is a talk that nobody would like to ever present, but here I am, and here we go. My name is Daniele Michilli, and a few years ago I discovered this source, this periodicity in a source detected by CHIME FRB. So basically, I found out that the separation between the multiple components of this burst arrived with a clear periodicity. And at the time, we spent a lot of effort convincing ourselves and the referees that this periodicity was real. And it suggested a neutron star origin of this FRB. Now, the zero hypothesis in the paper was that this could have been a galactic source, but we excluded the case because we didn't find in the direction of the source any evidence for a counterpart that could explain the high DM and scattering excess. Recently, a new subsystem of CHIME called CHIME's law came online, and Jeff will tell us all about this later in the conference. And this new system started finding a galactic pulsar that showed striking similarities to the previous source that we published. In particular, all the parameters that we derived from these 3 seconds of data are compatible with the galactic pulsar, except for the declination, which is 20 degrees off. So at this point, we're pretty certain that this periodic fast radio burst, we rediscovered a periodic pulsar, and this is just a galactic source instead. So the question we need to answer is why the declination was 20 degrees off and we didn't realize it. First, let me tell you that we found out about this just last week, but we wanted to inform all the community as soon as possible. And the analysis I'm presenting are still developing. We believe what happened is a heavy rain when we observed our daily calibrator, together with a particularly strong RFI and some probably malfunctioning of our software. All these rare occurrences together brought part of the band of the telescope to be pointed to look at the wrong direction of the sky. We daily check pulsars that are in our beam, and we didn't notice anything unusual on that day. And we believe this is because the problem was only in a small fraction of the top of the band, but this pulsar is highly scattered, and so is actually much brighter in the top of the band, contrary to most of the other pulsars. Again, we believe that this is a very rare occurrence, but we are currently investigating the problem, and before we panic about every single detection that we published in the past and that we are currently preparing, we are confident that the vast majority of our localizations are correct, but we are currently working to triple check that all our localizations are right, including those that will be presented in Catalog 2. So what happens now? We are in contact with the Nature editors, and we are discussing with them the next steps, and we'll submit a note as soon as our analysis of what happened exactly is completed. And as we've done that, we'll also put additional checks in place to prevent this from happening in the future. before a week ago, we didn't even know that this failure mode was possible and that our system could be 20 degrees off if this rare combination of events would have happened. So on behalf of the collaboration, I want to sincerely apologize to anybody that put effort studying this source. And again, we are working hard to prevent this from happening in the future and to triple check that all our localizations are correct. Thank you.
Thanks, Daniele. Do we have any questions?
There were two other slightly lower sources who were in the second generation quality here. You have there. Are they still genuine or do we have to take that?
Yeah, thanks for the question.
Sorry, can you repeat the
Yes,
question?
I'm having to get from Frankfurt. Yeah, I asked this question.
Can you repeat the question?
Yeah, absolutely. Sorry about that. Yeah, so the question was that in the paper we published, there were two additional sources that presented some form of quasi-periodicities, although not with the same significance. And the question was that if those sources are genuine or galactic as well. From all our preliminary checks, these sources seem to be genuine. They were detected on completely different days with different gain solutions. So we are confident that they are genuine.
So you and your team, this is Yuri van Leeuwen from Astra, you and your team have made many amazing discoveries. And so, of course, it's possible that sometimes a mistake gets made. And our field moves forward by many genuine discoveries, but it moves forward especially if people are transparent about what happens. So I really want to commend you and the team for standing up and sharing with us this result. And I think it's a big.
And I want to thank you for the very nice response. I wasn't sure I was going to get it. And it's another demonstration of how wonderful this community really is.
Okay, so